It's great to be here. I will be talking about all kinds of things. I hope you will find useful. The title is maybe not completely correct, but you will see actually what it will be all about. It's basically, I will be talking about making strategic plans reality. When we talk about strategic plans, we will of course particularly emphasize the software technologies in accomplishing the objectives of companies. And what we will do is that we will introduce a maturation process. That's a process to bring companies to better levels. I try to convince you by presenting a number of motivations why this could be good for the companies. Especially the last part of my talk will be more technical. So I will try to present this complex issue from all different kinds of perspectives. So assume that you are sitting on your comfortable chair and you receive a telephone call from a very important person. I don't know who's the most important person in Poland, but assume a minister or somebody like that, and calls you. No, not that important. Vice president or vice minister, I don't know, and says, given a set of potentially or strategically important companies, so assume that you have some national objectives and there are some important companies to accomplish these. So how to determine the strategic objectives of these companies? That means probably minister doesn't trust that much to these companies. He thinks that they're wasting too much money. How to turn the strategic objectives into tactical and implementation objectives, and how to steer all these. So of course a person like us or like me, probably this is a very unusual question to receive, or a set of questions to receive. I have been working for European strategic programs for about 16, 17 years. We're involved in many programs, definitional programs, establishment of programs. So I think, I suspect that was the reason why I received this call. So here are my answers. Of course, it was quite scary, but my answers were, okay, strategic objectives. I think companies should know this much better than I do. But however, they should really they should really understand what's going on in the world. And there are many businesses are changing. Software technology is crucial. So this was my answer. How to go from abstract strategic objectives to concrete steps. What does it mean, for example, for your research? This is actually a problem-solving process, going from abstract to concrete concerns. And how to steer? Steer, of course, steering this relates to the other 2 points. So what you could do is that classify companies according to their maturity levels, identify the current level, define maturation processes, and steer the overall process. So that was my answer. The problem of identifying levels of companies, of course, a company cannot be defined all the processes within a company at a given level. At certain different parts of company, different processes may have different kinds of maturities. But this was my answer. So I started a project in 2010, 2011. I'm a Turkish origin, but living in Netherlands for last 42 years. I never worked in Turkey, but this call was from Turkey. So I was asked to work on this plan. So I flew very frequently to Turkey to implement these objectives. So to do that, we have defined a set of levels. Introduction is when you start talking, actually you introduce. Transition is giving courses or talking to people. Description is actually try to understand the strategic objectives and to make plans to see what is missing or what you should be doing to accomplish your strategic objectives. We have integrated knowledge generation within it. That means company needs to gain certain amount of knowledge, or companies, they have to acquire this knowledge, adopt this knowledge, apply it to products. And leadership, here it means that they are so good in all these activities that they make this their usual processes. So in other words, companies continuously improving itself, making itself ready to changes and so forth. So the objective is to work towards the leadership. So actually it's like a feedback control cycle. You measure, evaluate, react, of course, within this context. So to do that, what we did was I have established a strategic research steering committee, defined the roles of the committee members, and talked to companies. And there was a coordinator, and multiple universities were involved. Basically, I have visited 5 companies in 4 years' time, actually almost more than 4 years. There were interruptions in between, but in total, from 2011 till 2017. And so we have developed a software engineering technology maturity model. It's not that much software engineering, it's more system engineering. It's a general methodology which determines, actually based on problem solving methods. So how does it work? So this has some unique features, and this report was agreed and approved by all parties. Okay? So how does it go instead of being desperate, because company strategic plans are very abstract, and actually the difficulties are to identify concrete obstacles, problems related to that. So what we did was we formed academic committees, a group of friends who are experts in different areas, related areas, especially in software-related technologies. And we visited companies, and we met. We asked companies to present their strategic objectives, and we have selected per company about 3 to 4 main strategic objectives. The idea is to make, in this particular case, because financed by Turkey, that they want to have their industry, key industries, to be leaders in the future, more or less try to form their own, how do you say, they want to have their own control in the key strategic technologies. Okay? So I think that's quite interesting. I believe this is also important for many countries like Poland. Instead of following the global orders, you could develop your own vision and own technology. So what we did was we worked with engineers. So I work with hundreds of different engineers. They were saying, for example, we do this and we do that and we want to do this. Then we are asking, do you know model-based testing? What is that? Do you know this? Do you know that? Do you know optimization methods? Do you know scheduling theory? All kind of fundamental topics that are useful to bring the company to a higher level. Okay, so instead of being desperate, we would like to have actually a concrete steps towards the future. And we worked with the terminology. We agreed on terminology, state-of-the-art, current return on investment. And actually, we also look their competitors, what kind of research they do. And then try to find out actually the PhD topics. For example, what kind of PhD topics Boeing is giving at this moment, or Thales, or whatever. And we came up with a number of documentations, reports with standard formats for us, which means that the topic, the problem description, challenges, state of the art, very concise. Basically not from the approach point of view, but problem description point of view. And in the end, this is quite important. We organized, so in the end, what you want to have is that companies have capabilities. Capabilities, I will talk about these capabilities also in detail. This will be more technical part. Capabilities, and we organize around the product lines. So, for example, you are aiming to build satellites, so we had a satellite product line. Why? Because in the end, we would like to actually progress further than adoption, value creation, and so forth, application, and so forth. So in order to do that, we had a bunch of research topics around each product line so that they could be applied within a product, okay? So especially for knowledge creation, adoption, and so forth. So each capabilities should be provided by university. So this research center is actually more like a coordination center. And then the companies are closely cooperating and the capabilities should be developing. So this is at least the objective, okay? And for example, only for knowledge generation, we had these state charts, and actually this defines the progress in a particular activity, and each transition was defined in certain conditions. This was all in the maturity book. So we tried to more or less standardize. This was described here, okay? So what are the technical results? I am presenting 4 companies here. The 5th company was Siemens, so it was not from Turkey. Siemens factory automation. I also applied the same plan for Siemens. And there we have identified 25 PhDs for Siemens. Siemens is considered as a world leader in factory automation, but the question is, will they remain as the world leader for the coming 10, 15 years? So this is especially, of course, for realizing strategic plans for the mid-term and long-term. I'm not presenting it here. These are the companies, and these are the projects, onboard systems. These are onboard systems for Boeing and Airbus, entertainment systems, simulation systems, fire simulation, helicopter simulation, for example. These companies have products there, but they want to be more in a leadership position. Mission critical systems of systems. These are actually flight control, aerospace management and control systems, avionics systems. So what you see is that these are large safety critical systems. So satellite systems, so I didn't know that much about satellites, but of course many technologies we know come there. So I have seen how they build satellites. So for each project I work 6 months, about 5-6 months. That means so we have defined these PhD topics and everybody approved. So these are 150 PhD topics we defined. Plus I did also with one second company, radar systems, 10 more PhDs there. So it's about 160 PhDs. And these PhD topics, we also met 29 professors around the world and talked to them and asked their feedback and if they want to join to that. That was also, I had some of my ex-students, they are also professors now, involved in this, plus some other experts. So we really had a team that worked with. When we classify the activities, this is of course adaptability and reuse. This is of course a classification. You can classify in many different ways. Adaptability, reuse, model-based verification, because many of these systems are safety critical systems, but these projects are multi-billion projects, okay? So the projects are of course very impressive. These are more or less the classification on topics. Of course, you could classify in different ways. So what is good from researchers' point of view? We know that companies need to do research more and more, especially if you look at the topics that I'm talking about. You really need very high advanced technologies, and companies don't have time or resources or capabilities to own this knowledge to make these high technology products. We know that writing grant proposal is very boring and very time consuming, and most of the time we may not succeed. So our view is that, well, this should be good from a researcher's point of view, because we approach actually researchers. Assuming that we are fair, of course, we should be fair here, okay, not to make ourselves rich only, but to make companies better. So we assume that we have some ethics in that. So the researchers don't waste time, but of course, they have to adapt to the way of working. So that means in all these processes, so are we done? No, we have to also understand the recent trends in industry. So I would like to have second motivation, why this is good also for industry from the perspective of the current trends that we observe in industry. Okay? So what we see is that I have a paper included in the proceedings, so I wrote these and I gave references to all these points. We have now knowledge-intensive manufacturing instead of labor-intensive. Traditional industries, you know, these heavy big factories, workers are working and so forth, and these kind of technologies are changing. We have more and more, of course, knowledge-intensive manufacturing. We are really focusing on intellectual property rights and managing knowledge instead of resources and labor-intensive manufacturing. The portfolios, traditionally big factories manufacture for years, standard, well-defined products, but now we have to be multi-portfolios, dynamically optimized. We have mass customization instead of mass production. So this is quite also a different concept. That means actually, although we have mass production, which can be customized for different customers, this can be only possible, of course, with software technology, computer technologies. So this is actually quite interesting because when we look at the ideas of labor and socialism and capitalism and all these things, actually, this is a different model. This requires a different model than traditional models of course, who owns the rights or labor and capital and so forth. So I think we need the new bright guys to write books about these new business models. Like 150 years ago, we had some very influential books about these topics, of course, and many wars. Proactive self-organizing companies, we need end-to-end alignment on optimization processes. Traditionally, you try to optimize, for example, efficiency of one production stage, but now we are really interested end-to-end, the whole process, and even after delivery, of course. So it's a continuous cycle, multidisciplinary use of team personnel, organizing business enterprises globally. We don't want to have isolated hierarchical organizations. Many of the items I list here are consistent with what Jan Bosch presented, with a different, slightly maybe sometimes different terminology, but actually the businesses or the products that he was describing very much actually fits into this way of producing. Improve time to market, because money is very important, time is important. Extensive use of state-of-the-art. The last 2 points are that we cannot realize these technologies without computer science, without software technology. So it is not just another technical skill, but it is the main enabler, okay? So we should realize that. So in other words, every company in the future will be a software company. This is, I think, more and more true every day. And universities are are very important, especially to implement the technical detail. So we cannot debug reality. We better accept these facts. So there is, of course, Industry 4.0. We hear more and more. It's a more political kind of movement, especially initiated from Germany. And there are, of course, many publications about that. So it's about interoperability. That means sensor devices, machines, and people are connected together. So efficiency should be high. So when we look at the benefits, they say it should be much more effective and maintenance should be much better, improved because of the autonomy, intelligent processes, and so forth. So I don't want to repeat this, but they claim that it's the fourth industrial revolution. So I try to present my slides independent of 4.0 because we want to also evaluate 4.0. So in that sense, we have to be more general, or we have to have a more global looking. Our view is that, yes, the concepts of 4.0 must be understood in the process of ongoing transition. So I think no transitions are revolutionary. It is a continuous process. So we cannot say that it's a fourth revolution, because many of the things that Industry 4.0 are referring to actually were happening. But if it is even more than that. Therefore, I call it Industry 4.0 and beyond. So the points that I listed, I prepared them independent of Industry 4.0 definitions. So therefore, I call them Industry 4.0 plus more. Okay, yes, but we shouldn't really, especially academicians, work with hypes. We should really try to be more fundamental or conceptual. So I'm not saying no to Industry 4.0, but we should understand it in the global process of industry changes. Now, what about universities of today or of the past? Well, basically, you know, we have research, education. We should also put their administration probably work. I have been chair and department head for 15 years. I know administration work is many more times than other activities, but okay, we don't want to confess it always. But the difference is that here it's more or less in very traditional universities, research is disconnected. You are not really tied to solve real problems of industry. Of course, there are always some forces to force you, for example, due to calls and grant proposals you have to write and so forth. But in traditionally you are, historically we are loosely connected to what is happening in academy. This is a traditional university. Of course, it depends how you define it. But really, in order to support companies, especially the maturation process which I have described, we have identified 160 PhDs, and these are very important for industry, in the end, for the country, to accomplish their strategic objectives. And if you really want to be a part of it, we want it or we don't want it, we like it or we don't like it, we have to somehow also change. So universities are meant for new ideas and bright ideas and change in society, but traditionally and in many places they became actually obstacles for change, because it's difficult to implement many of the new ideas probably. So of course many of the items can be considered controversial, but I'm looking this problem from the perspective of companies that are trying to accomplish their strategic objectives. So if this is our objective, in the end, the objective of the country where you are living in, then these should be somehow implemented. Okay, so Society industry needs must learn to work together in multidisciplinary teams, must be proactive in forming networks, must be flexible to adapt in changing demands, okay? Education must be also more about problem solving, critical thinking, multidisciplinary projects, communication skills, and consciousness. Of course, ethical concerns are also important. So not necessarily you focus only on teaching yet another optimization technique or graph search algorithm, but try to put it into problem-solving context and try to learn the material really to deal with complex problems of today and the future. So also universities must create suitable organization structures that all these things can find its place. So in other words, instead of making maybe strict points like we are doing, how many publications and so forth, you have to also appreciate if academicians work as I stated in this way. Otherwise, of course, they won't work or they won't contribute to industry and society. Okay, but they are important quality attributes: relevancy, alignment with the current state of the art, cross-fertilization. What is important is industry as laboratory. From company, it's an innovation. For universities, it's industry as laboratory. Then you can use industries as laboratories. And we find it very important to establish an academic research steering committee to guide the whole process. So for computer science, we can say that it's the main force. There is almost no product in the market which does not contain software or not produced by a process controlled by software. So that means 99% of products are like that. So it means computer science and software is essential. So this is also not debugging reality. These are the facts. These are the facts that you cannot control, like industrial developments, and these kind of facts you cannot really control. It's under nobody's control. Okay? So we have, of course, converged more or less when we look at the academic research programs. Many times these are hypes. We just, of course, many academicians want to get PhD, study, publish, and so forth, because this is the main force. But we, as I said, we really have to understand these as a whole, but also individual specializations, problem solving, critical thinking should be the actually main force of applying and researching these techniques. I would like to emphasize the last 2 points. Work on algorithms or solvers. You can either write explicit algorithms or you can do more declarative, have constraints, and you can define solvers, which means algorithms are maybe implicit. And also all kind of research to improve software qualities. These I would call techniques or the knowledge that is necessary for any other technique as well. So these are more or less what I would call cross-cutting techniques. So therefore I would focus on software engineering and technology. Why? Because in the end, we have to have economic production of software. You may have very bright algorithm, very bright solution, unless you apply it in some way and you gain value from it. It means there is a company, for example, making products out of it, and unless you maintain it, you turn it into money, nobody will use it. Okay? So we have, for example, a project with Canon, and they said to us, well, they are bright. It was about energy reduction in machinery, big machineries they built also. They say, well, many academicians come with bright ideas. We have already difficulties in maintaining our software. If we put everything they want to put into our system, we can never maintain. So it becomes so complex because they say, okay, measure energy of every part, and then everything should be gathered and connected, so you get a huge spaghetti code. Architecture is completely unmanageable. So therefore, we need to really consider for whatever we do, whether it's big data or machine learning, whatever, you have to really consider the qualities of economical production of software. Otherwise, it will not turn into a product or a value or a service. So therefore, I consider these techniques crucial. No matter how intelligent the software solution is, if it cannot be realized with the desired quality attributes, one cannot expect an economical value out of it. So then I will also, it's also my specialization, I will now focus on the technological aspects from software technologies. So I think, so what is my base? About 185 PhDs. I worked together with 5 companies. I showed you only 160 very briefly. Okay, plus Siemens 25. When we look at them, of course, we are more or less having here. This is our, for example, recent paper. I will show you a bunch of papers. This is a product line for reusable schedulers. We published in a scheduling conference, I think last week. This, for example, these techniques are used by a company that produces radars, and they build 35 different kinds of radars. And they all have slightly different techniques used, adopted, so you cannot develop all these products individually. Okay? So, for example, we are developing software for airports or any other factories where you have scheduling in some way. Scheduling is a very important technology. You may have many different kinds of schedulers. Even if you build, for example, elevators, you may use different elevator scheduling techniques to build them. And this software which we have developed partially is 900,000 lines of code. So it's very hard to develop all these things from scratch. Of course, we didn't write all the code, but we built a library around it. We are going towards systems of systems. That means that when you build a system, then it will be always used in a larger context, and you have to consider it. Many of these projects, almost all of them in fact, are used in a systems of system fashion. What does it mean, systems and systems? That means that you have to define systems in basic functions of the systems, or the evolution. You have to build in evolutionary functions or protocols, which I would call closure property of systems. That means that your system will always should provide certain evolutionary protocols so that it can be integrated in a larger context. So you shouldn't have the top. We always more and more ecosystems. Ecosystems can be implemented in different way. I have been working with large companies. Within a company, you could have also somehow ecosystems. We have adaptive control architectures, auto-adaptive. Instead of having traditional components, we have more and more components become adaptive. That means components are built in adaptation mechanisms to, for example, adapt to changing context. I am also presenting our important papers maybe in this context. So in all these areas I have been also doing more or less to some degree some research. Components, of course, not only adaptation will be component basis, but it could be a cooperative or peer-to-peer control, collaborative master-slave control. So different strategies are possible. In principle, more and more algorithms should be written in such a way that we are going towards almost in all these applications, distributed problem solving. It means we don't have centralized algorithms anymore, but algorithms should be written in some way, such a way that they should be cooperating for the obvious case of distribution, for reliability and so forth. The question is model-based development. Even I had meetings with companies in the Netherlands. They say we don't want programmers, we want modelers. Modeling is now, before they were saying, okay, nobody has the models, but when we look at now, even companies have excessive models. That is another kind of problem. And so models are, so my estimation is that programming now is used 30% and maybe 70% models, and model code is generated from models. For example, our schedulers, which I presented, the paper which I mentioned about, it has 7 domain-specific languages within the scheduling domain. So one can define, for example, task, the other one resources, the other one policies, and so forth. And actually we generate code from it. So because companies are more and more specialized, because it's a product line approach and so forth, you are going now towards more and more model-based development. Here is a paper, it's not a new paper, but we describe here how we derive models from domain knowledge. Basically, it's based on concept analysis. It's like theory forming. You can define models by analyzing the background knowledge and so forth. We are going more and more multi-objective optimizations. We apply this also when I'm presenting this, it's somehow consistent with my past research, but also many companies have these kind of, many projects which I have mentioned about, this 160 PhDs plus 25 more, many of them have some optimizations of certain qualities. We cannot optimize anymore it doesn't make sense to optimize for one quality, for example, for performance, because it's always trade-off. If you have performance, then maybe you degrade, availability or memory usage or whatever. So adaptability maybe. So for example, here we have, this is applied to Canon, the Canon project, energy reduction plus efficiency, precision. So the machine computes actually the best trade-off on the fly based on multi-objective optimization techniques. Also a lot of architectural issues plus a bunch of formal methods and mathematics and so forth. We are going more and more modularization of semantic concerns. Traditionally we had object, functions, and data. Object orientation was a data abstraction, right? And then we build their inheritance and whatever, polymorphism and so forth. But now we are talking about models, and models refer to some semantic concepts. Okay, for example, we have a traffic system, or we have a simulation of a fire simulation. Fire grows and shrinks, right? So we have really semantic models there. Where it's even the boundaries may not be fixed. These are called so-called emergent modules or emerging concerns, more and more important. And we need new semantic-based abstraction mechanisms. Here is a paper which we wrote, and I work on emergent properties after aspect orientation. I did a couple of publications on that. And we need really rich set of composition mechanisms because software should evolve and adapt, and we have, as Jan told yesterday, also more and more functionalities are introduced every week, every day, every month, so we have to deal with it. Another thing is that really we have to integrate verification techniques because they are mostly complementary. One has more false positives, negatives in one context, the other one less, so they complement each other. In other words, static checking, dynamic, for example, runtime verification combined with, for example, model checking and so forth. So the problem is, of course, if you have many verification techniques together, you may have too many models, which you don't want. So you try to use also same verification model if possible. Here, for example, we do model checking together with runtime verification in this paper. Also, it was an industrial project. So conclusions. What I try to do is actually I try to present the trends that we cannot control. These are technology changes in industry, and also software becomes more and more important. We have positioned 4.0 within this context. It only addresses part of it, okay? But so we have to think in a more global context. We have defined a company maturity process and applied for it. It's a huge work with many engineers, and 5 years' time. We have documented this in a number of publications. We have applied this process to 5 large companies. And we have evaluated trends of computer science and software technology. I have included the article there. All the references are given. Of course, the last part is more subjective because it's my research about the systems and so forth. But I have, after doing this industry work with many partners, I'm more convinced about these software technology trends than even before. Thank you very much for your time. I appreciate it.